Calorimetry is the measurement of heat transfer during physical or chemical processes. It relies on the principle that when two bodies at different temperatures come into contact, heat transfers from the hotter body to the cooler one until they reach equilibrium. The total heat lost by the hot body equals the heat gained by the cold body, assuming no heat is lost to the surrounding.
The equation Q is equal to mc delta T is used to calculate the amount of heat transferred to or from a substance. Here, m is the mass of this substance, c is its specific heat capacity, and delta T is the temperature change. If the temperature increases, heat is absorbed. If it decreases, heat is released. This equation is applied in colorimeter experiments to determine heat exchanges, using the conservation of energy where heat lost by one substance equal heat gained by another.
For now, let's consider this example. A 5 kilogram system is heated from 30 degrees Celsius to 60 degrees Celsius with a specific heat capacity of 0.45 kilojoules per kilogram Celsius. For now, we will calculate it using the formula Q is equals to mc delta T. For now, we should find delta T since we all other factors we have in the problem already. So first delta T, to calculate delta T, we will use the formula final temperature subtract by initial temperature. In this example, our final temperature is 60 degrees Celsius and our initial temperature is 30 degrees Celsius, which we will get 30 degrees Celsius all in all. Now we will just have to substitute m, which is mass. We have 5 kilogram times the c, which is 0.45, then times by the 30 that we solved before, which is delta t. All in all, we will get 67 67.5 kilojoules. Oops. 0.5 kilojoules.
In summary, calorimetry uses the heat transfer equation to measure heat exchange during temperature changes. It based on energy conservation where heat loss equals heat gain in an isolated system. Understanding this allows in determination of specific heat capacities, temperature changes, and calorimeter results in both physical and chemical systems. This structured approach enables precise heat transfers calculation in practical application and experiments. In bomb calorimetry, the sample is combusted inside a sealed bomb vessel filled with oxygen. Because the volume is constant, no expansion or contraction, the heat measured corresponds to the change in internal energy rather than enthalpy. The heat released by the combustion is absorbed by the water and the calorimeter, causing a temperature rise. The total heat QQ absorbed by the calorimeter system is calculated as where Ccal is the heat capacity of the entire calorimeter system, including water, and and delta T is the temperature change of the system. Since the heat is measured at constant volume, Q equals delta U, the change in internal energy.
Now for this example, if the calorimeter has a known heat capacity of C cal is equal to 10,000 joules per degree Celsius and the temperature rise due to combustion is delta T is equals to 2.5 degrees Celsius. The heat released by the sample is, which will be the same formula as before, which is no different formula. For this, we will use Q is equals to C cal times delta T. We just go straight to the solving because we already have every given that we need. So C cal is 10,000 kilojoules times that by 2.5 degrees Celsius. Now, if we put this on a calculator, we will get 25,000 joules. And that's it.
Bomb calorimetry measures the heat of combustion of a sample at constant volume by recording the temperature increase in a water bath surrounding a sealed combustion vessel. The heat release is calculated from the calorimeter's heat capacity and the temperature change. This makes it a precise method for determining internal energy changes and calorific values of fuels and food samples, critical in thermochemical analysis.
The standards of enthalpy of formation is defined as the enthalpy change when 1 mole of compound is formed from its constituent elements of their most stable form under the standard condition. It is a fundamental thermodynamic property used to understand the heat change associated with the chemical reaction and is expressed in units of kg mole.
Number 1. The goal is to find delta H for a specific reaction for which direct data might not be available. 2. Use given reaction whose delta H values are known to piece together the target reaction. This may involve reaction reversal or scaling. 3. Reverse a reaction. Change the sign of delta H. Multiply coefficient, multiply delta H by the same factor. Add the adjusted delta H values of this component reaction to get the overall delta H for the target reaction.
Now, the formula is delta H of reactions is equals to the sum of delta H for products minus the sum of delta H for reactants. This means the reaction enthalpy is obtained by taking the difference between the sum of standard enthalpies of formation of products and that of reactants, weighted by their stoichiometric coefficients. And now, for the summary, standard enthalpy of formation measures the enthalpy change when 1 mole of a compound forms from its elements at standard conditions. Hess's law leverages this concept to calculate reactions enthalpies by summing standard enthalpies of formation of reactants and products. Through this, reaction pathways can be constructed, enabling the determination of enthalpy changes for complex reactions that are not directly measurable experimentally. Now, for this example, if the calorimeter has a known heat capacity of C cal is equal to 10,000 joules per degree Celsius, and the temperature rise due to combustion is delta T is equals to 2.5 degrees Celsius. The heat released by the sample is, which will be the same formula as before, which is no different formula. For this, we will use Q is equals to C cal times delta T. We just go straight to the solving because we already have every given that we need. So C cal is 10,000 kilojoules times that by 2.5 degrees Celsius. Now, if we put this on a calculator, we will get 25,000 joules. And that's it.